Great to see you. Just in time, 9 o'clock in Switzerland, 8 o'clock in UK. So, I think everybody joined. So, good morning and welcome to a cross-country edition of aiLights. Hoi from Switzerland.
Hello from the UK.
Your hosts today are Sabine Wildemann from aiLights, where we connect stakeholders within the Swiss AI community and support knowledge transfer on AI, and Mike Romano from Oxford AI Society Entrepreneurship Hub. Mike works across applied AI topics and he bridges ecosystems within the society. He will moderate today's panel. So, Mike, over to you.
Thanks, Sabine. First of all, thanks to you and the whole aiLights team for making this collaboration with Oxford AI Society happen. It's great to kick off this together. We're joined today by two people working hands-on-hands in robotics from the UK. Lizzie Mushangwi, a Dr. Phil candidate in materials science at Oxford University and team lead of the Hardware Lab and Entrepreneurship Hub at the Oxford AI Society. Lizzie, hi.
Hi, everyone. Nice to meet you. Thank you, Sabine and Mike, for having me.
And from Switzerland, Dr. Jorge Peña, group leader in robot learning at the Center for Artificial Intelligence at University of Applied Science Zurich and co-founder of Binabik. Hello, Jorge. Welcome.
Hi, morning. Thanks a lot, Sabine and Mike, for having me here.
It's great to have you both here.
Hi.
Today we'll focus on robotics and embodied AI beyond what we see in headlines and on social media. And we look what's actually happening in practice. Our session is titled, therefore, Demystifying the Hype Around Embodied AI. We'll hear from our two guests as they share concrete systems they're working on, from robotics arms at Oxford to mobile robotics and field deployments at University of Applied Science Zurich. And then from there, we want to look at what actually holds up when systems move beyond controlled environments. So it's where constraints really begin to show, whether that is in hardware and data integration, simply deployment. We'll also touch on what generally scales today, where things still push back, and where it makes sense to focus on. Let's say for our audience here is interested to build something deployable right now, we want also to elaborate on that. That's roughly the lens we're working with today. Sabine, I'll gladly hand back over to you.
Yeah, thanks, Mike. So some notes before we start. So this session is being streamed, as always, live on YouTube and on LinkedIn. You are invited to drop your questions in the chat on the right side. We will do our best to answer the questions during the session. And we will have presentations from Lizzie now and Jorge after that, and followed by a panel moderated by Mike. And at the end, we will have about 15 minutes for your questions planned. So I was just sharing this with Lizzie and Jorge. The background here stems from a dream I just had some days ago when I was dreaming about that session. And while I was talking, robots were working behind me in the mountains. So we thought maybe it's a good idea to have this from UK and Switzerland. So let's jump into the topic. And Lizzie, the stage is yours.
Perfect. Thank you. I'm going to share my screen and then ask you all if you can see it. Yeah?
Yes.
You can see it, then
Yes.
I will go. So hi, everyone. My name is Lizzie. I am a final year PhD student in material science at Oxford here. I also lead the hardware and robotics work in the Oxford AI Society. And today I'm going to talk to you about what it looks like to build embodied AI capabilities and systems in practice, but not just in a lab with unlimited systems and resources. We're a student society, so we have real world constraints and we want to work with like real people, real hardware, and start learning from scratch. So my background is in physical systems. I'm a material scientist and a mechanical engineering bachelor's, if you want credentials. So when I entered the AI space, I noticed a lot of intelligence was happening in software, but very little of it was happening in the physical world. And this is where the hardware lab came about. So today I want to frame this topic to you from the perspective of how to lower the barrier of entry into robotics yourself. There are many more advanced clubs and societies, but if you're interested and you're a beginner, you can see the journey that we took to get to where we are right now. So we built this hardware lab because we kept seeing the same pattern. Students were very strong in software and very capable in training models, but almost had no exposure to what happens when AI touches the real physical world. So when we launched this lab, 180 people signed up almost immediately. It was like in 5 days. We only had a space of that could fit 12 people maximum. So immediately we hit physical constraints. And from an internal study that we did, 98% of the people said that they were interested in robotics. And the first constraint that, like I said, was physical space. And we were quickly zapped out of the software realm and into the physical realm. And everyone who we talked to had no experience assembling robots, calibrating motors, or simply even knowing where to start. So AI today is very software heavy, like I said, and it's largely driven by benchmarking, improving metrics, and then publishing this result. So what's missing is that deployment intuition. And in the robotics and deployment, that's where friction appears immediately. So the lab is an intersection of communities. We have OXRAM, which is Oxford Robotics and Additive Manufacturing Society, and OXAI, which is what I work with. And the first lesson that we learned was to collaborate and share knowledge. So we have students who are strong in 3D printing and additive manufacturing, and then we heavily drew from experience from OXRAM in order just to initially get running. So if you're a beginner, definitely lean into networks that already exist. So OXRAM really helped with us in terms of prototyping, 3D printing, and OXAI is very software heavy. So we were strong in terms of like the machine learning and the neural networks and training the models. So it was kind of like a intellectual transfer between the two societies. And this enabled us to expedite the work that we were doing. A lot of the public, so what is embodied AI? I think it's great to start on a level playing field. A lot of the public conversations that we have around robotics focus on humanoids or general intelligence. But that's not where the most successful systems are today. I think, in my opinion, the systems that work the best are constrained systems, like arms that work on smaller tasks, or arms that will be doing surgery, or robotic dogs that will be working in the nuclear or defense area, and drones. Some mobile robots that operate in structured environments is not just what we focus on in the hardware lab, but this is what kind of zaps everyone's attention when they think of robotics. So one of our goals was to help students internalize this difference really early. And if you want to lower the barrier to entry to robotics, the second rule or lesson that we learned is to start constrained. So we started with a humanoid arm, and we started with a very, very simple streamlined task. So we instead of doing 10 tasks all at once, a single robotic arm, and this was a simple pick and drop thing, what we wanted as our final goal. So our hello world, what we called it, was to have a robot that picked something up and dropped it down by ourselves. From there, we could springboard into something more interesting. Okay, and so to achieve this, we relied heavily on open source infrastructure, particularly LaRobot. I'm not sure if you've heard about it, but this is an open source GitHub and Hugging Face repo where you can assembly, plug and play, and build a robot by yourself. It's like adult Lego. So this was lesson 3 that we learned. And it was kind of the inflection point or the catalyst that helped us to really expedite our progress. The key advantage was just the pipeline was streamlined, and the GitHub repo just enabled us to get it running. So all of our decisions were made to force everyone through the full loop. So everyone learned how to assemble, calibrate, data collection, training, deployment, debugging. And once you go through this loop, once your understanding of AI shifts, you really realize that many model problems are more physical problems, and many data issues are just calibration issues. So this requires like a lot of just iterating and going back and forth. And once you go through this loop once, your perspective of the difficulty of AI changes. Is kind of this is what kind of lowered our barrier into entry by just going through this iteration procedure. I'm not sure where that came from. Yeah, and one of the most encouraging outcomes was how quickly students progressed. So roughly over 8 weeks. Oxford terms are quite short. We have 8 weeks, and this is spread over 2 terms. Students went from zero experience to assembling robotic arms and calibrating motors and collecting data and training simple policies. And this kind of was really like heartening to see. The goal was not production ready robots, but just ingraining that capability and know-how from beginner experience, and just getting to a stage where you could say, oh, I know how to build a robot, I know how to train a model. And so I think capability will scale faster than hype. And once people understand these constraints, they can learn about what is realistic. So from what we're seeing, we're having debates about, will humanoid robotics even be integrated into society? Where is the role of a fully formed humanoid? Maybe we just need an arm or a head or some specific part of a robot that will be used in society. So it's good to see that these conversations are happening and students are starting to use their critical reasoning to think, do we actually need a human representation to be walking around in the world? Yeah, and one thing I wanted to emphasize that we're not stopping at this first successful demo. We're trying to complete this loop, and then we've assembled the arm, and we want to move on to other systems as well. So I have students who are interested in moving away from small scale teaching the robot to play chess, but more ambitious students want to maybe make a wet lab and have an automated robotic arm that can do biology. I'm interested in high throughput material science, so I'd love to make like an appendage to this robot to enable it to do high throughput manufacturing. So we're at that scale now where everyone is kind of leveled up. We're all beginners. We've demystified the hype. We've learned the basic skills to build these robots, and we're trying to branch off into something that's actually world impactful and changing and scalable. I'm not sure if that was 10 minutes or 15 minutes, but it's me. If you
That was great.
Only 5.
It was great.
15. All good, all good.
But yeah, if I was
Was
to
that
summarize from our
perfect?
experience, to lower the barrier into entry, definitely start constrained. You don't need to do like a full embodied human. We chose an arm, and that really drastically lowered our entry into this route. Use open source. I highly recommend Robot because that has a fully outlined pipeline on how to assemble a robot and then train the policy and then iterate, and then you just keep going from there, and then you're immediately from a beginner to an advanced person, and collaborate across disciplines. Oxfam really helped us, and we're moving away from this from basic PLA and plastic manufacturing to trying to build more metal ones and more arms that can build higher loads. Yeah, force yourself to the entire loop just to learn everything, and embodied AI will become less intimidating once you've experienced this entire loop, and from there, much more interesting things can become possible. Yeah, thank you.
Wow, thanks, Lizzie. That's a really helpful look into what's actually happening inside the hardware lab, and it's also great to hear you help ambitious students to level up, a bit with you and focus on simple pickup tasks, forced everyone through the full loop, and then you'll decide. We'll come back to that idea of deployment intuition and also open source you touched on in the panel. Let's maybe move now to the applied perspective from the Swiss Center of Artificial Intelligence at the University of Applied Science, Zurich. I'd say if we have like maybe a question in the audience, we might be able to ask Lizzie a question. Do we see something? Otherwise, I'll ask you a question. So you asked about the data integration, Lizzie. Would you be able to specify a little bit on that? Is it because of also training issues that have constraints in the lab?
What do you mean by
then
the
you cannot
data issues?
You did say that basically there's going to be also data integrated into this project, into the low robot. And would you say that the data layer was more important to go full training with the robot, or was it more the physical constraint?
I feel like it's more the data, because as soon as you take this arm or whatever you're working on out of the very constrained and fixed environment that you put it into, the model starts to break down so easily. So it's always like data, what goes in, and what's it, crop data in and crop data out. So definitely data constraints. I'm not sure how we can expedite that. I've read some articles on possibly simulating environments and using simulated engines to simulate like a real world model, and then just training a model on that instead of having to actually, because we use a camera and that camera tracks what's going on, and then that's translated into actual movement. But data constraints would be the main thing that would break down our model, not physical constraints, because that would be an engineering problem, and I feel like we engineer things to quite tight tolerances, and it's easy to account for those. But if you take your robot into a sunny room, but you trained it in a dark room, it may change like how it interacts. So definitely data issues.
Great context. Thank you. So helpful. Jorge, the floor is all yours. Applied perspective from the Swiss Center for Artificial Intelligence at the University of Applied Science.
Thanks a lot, Mike.
Would you like to give us a little bit of an introduction to you and your project you're focusing on?
Yeah, for sure. So yeah, thanks a lot for the intro, Mike, and thanks, Lizzie, for the presentation. I think it will make for a very nice connection. So I don't define what embodied AI is, but directly go into it. So that helps a lot. And I will also touch a lot on basically the fragility around data that we have today. So build on that. And as well, I liked that you raised the question of, do we need the human form? And even though we see a lot of humanoids around, is that really what we need? But if I start with a short intro, so yeah, thanks, Mike. My name is Jorge Peña. I lead a research group at the Zurich University of Applied Sciences at the intersection of AI and mobile robotics. My background is more on the robotic side, so I've been 10 plus years building many different types of robots, working with drones, ground robots, and tiny swarms of tiny robots. But for most of those 10 years, my focus has been on applying machine learning into robotics. And of course, the last 2 to 4 years, especially since ChatGPT came out, this has taken a new dimension. There's so many possibilities. Maybe a short disclaimer, let's say, about this talk. I will give, as Mike said, a very applied perspective of what is possible today from, let's say, a more industrial perspective or real use case. I cannot cover in 15 minutes the entire field. So just to say that basically on the research side, to many of the challenges that I will be presenting today, there's people giving answers already, but I see that that's still a little bit far away from seeing real world applications, especially in industry. So a little bit of context about me or my lab. So these are the main robot platforms that we have at the lab today. I've been here for 6 months now, building and leading this new lab. So it's not really limited to leg robots. So here we only have humanoids and quadrupeds and then robot arms. But this is the first thing that we have today. And there's massive interest from industry in trying all of these platforms. But I also am interested very much in basically bringing all this new wave of AI, for example, into assistive robotics. So working with companies that make intelligent wheelchairs, adding robot arms, let people interact with them easier. So I feel that there's a lot of progress in AI that is going into fancy robots and not so much into actual useful use cases. So even though this picture shows these fancy robots, that's not the entirety of my focus. And given that intro, so delving directly into the topic. Jensen Huang said last month in Las Vegas, or a bit more than a month ago, that the ChatGPT moment for robotics is already here. I mean, so many people have been saying that it's around the corner any moment now. And while I agree that there's been unprecedented progress in the field in the last few years, I have to mostly disagree with this statement. And the reason is that for me personally, what the ChatGPT moment meant for AI in general is mainly two things. One, that AI became accessible to anyone. And this is actually changing in robotics, as Lizzie said, with projects like Le Robot. So hardware is really becoming accessible. But with ChatGPT, what we also had is that anyone could take general AI model, ChatGPT, and ask it to do anything. So we had a robot, basically a model that could do anything for anyone. I don't think that's true with robots. If you take the most advanced humanoid robot or any platform, robotic platform today, no matter which one, whether it's Chinese or American or European, and you put it into a new factory floor and you ask it to do anything, if you are lucky, you can ask it to, hey, can you do a step forward or can you dance? But if you ask it to actually pick up a new object in a new environment where it hasn't been before, it probably can do zero. And therefore, I don't think that we are there yet with this ChatGPT moment in robotics. Now, again, as I said, to give a bit of context of what we've seen, so these are videos picked up from the last year, the progress has been unprecedented. So this is already nearly a year ago. This is Google's Gemini Robotics. It's much better now. It's more agentic. It's now a multi-layer AI model. But in terms of manipulation capabilities, yes, we can do impressive things. This is also from last summer. Now Figure has shifted to home robots, and you've probably seen a video from a few weeks ago where it unloads a dishwasher. So we have, again, unprecedented capabilities in terms of manipulation and also what we call local manipulation with, for example, humanoid robots or robot arms. And everyone is pushing in this direction. So NVIDIA is putting a lot of work, for example, also on being able to learn in simulation. But a common aspect of these three examples here, for example, and I will emphasize on this, is that these tasks are short in time. So there are very, very few videos out there. You will find very few examples of robots doing something continuously for minutes at a time, or tasks that require planning for, let's say, more than 5 to 10 seconds. The second thing, and I will build on that in a moment, these robots are not moving too much. And the last thing is that these basically, as Lizzie was saying, there is a data problem in the sense that these three examples are trained mainly, largely from human demonstrations. Now, there's a lot of work being done in being able to basically use and leverage more data, but today, the majority of this is done by teleoperation. So people wearing VR headsets, for example, or gloves or suits, and then operating the robots. Then on the other hand, you've probably seen a lot of videos and demos like this. So very mobile robots, impressive, let's say even superhuman physical capabilities, whether it's Kung Fu with a humanoid, a robot dog doing all sorts of parkour and acrobatics, and even teaching robots to show emotion or emotiveness. So I like to show this example from Disney because it really contrasts a bit to what we typically see from other companies, while it's still the same type of methods. So we have robots with impressive manipulation capabilities. We have super agile and mobile robots. Now, the first problem here is that these two basically source of capabilities for robots come from two different fundamental methods in AI and robotics. So the first three examples I showed are basically what we call foundation models in robotics, something like ChatGPT. And today, this is largely learned from human demonstrations. So they are limited basically by the amount of data and the type of data that we can generate. And I'll build more on that in a moment. And then we can do all this fancy stuff, which we do mostly in some simulators, where you can teach a robot to do basically almost anything that its hardware allows, whether it's Kung Fu, parkour, or showing and transmitting emotion. But this is something that we do with simulators. And this means that these three robots here, for example, these three examples, the Kung Fu, the dog, and even Disney's robots, are not aware of their environment when they are deployed in the real world. They don't have really obstacle avoidance. If you put a little kid or anyone or any object in front of one of these robots and you activate this Kung Fu policy, they won't see them, they won't stop, and they will crash, basically. So we have two fundamentally different ways of training robots today. And again, as I said, there is a lot of research on merging these and on leveraging both. But today, in terms of real world and deployment and applications and use cases in industry, we have these two fundamental differences. So basically, taking this into account, why are robots not there yet? So I will just shine light into a couple of aspects. So this is not exhaustive, but a couple of examples of why robots are not there. And the first one is what I will call here the human in the loop limitation, taking a bit of flexibility in the use of the term. So for many, many years, at least from an academic perspective, when you talked about human in the loop robotics, this was a good thing in the sense that it was not just a robot that would perform by itself, but you could basically keep oversight, or you could introduce human preferences, or you could have a human in the loop in the learning process. So this was a good thing. I would say that today the human is the limiting factor. So why don't we see this here? Gemini took a bit, was very imaginative, adding extra arms to the robot, but basically, why don't we see robots with 4 arms or 6 arms? Well, the main reason, in my opinion at least, is basically we don't know how to teach them yet. And this is an example. There's a lot of videos online about robots pouring a drink. And this is how a robot opens a bottle. Now, this looks very familiar because this is how we open a bottle, right? But most of these robots have so many motors in their arms that they could just place the hand on top of the bottle and screw within half a second the lid. Now, they don't do this because we teach them from human demonstrations, and humans cannot do this. We could teach them in a simulator, but then we would need to build let's say, purpose-built simulator with a lot of different types of bottles, a lot of different types of environments, where we could use reinforcement learning, basically, to teach them how to more efficiently unscrew bottles. So we are really limited by how we teach robots. The hardware can do so much more, not just in terms of doing Kung Fu and parkour and fancy acrobatics, but also in terms of manipulation, but we are not able to exploit it because we don't have the way to teach them. Then there's also what I would call the scaling gap. We've had pilots for more than 2 years already, or at least the last couple of years. So this is from July 2024. Figure announced their first collaboration with BMW. You can see from the previous video to this one that the robot has changed significantly. So this was really like a prototype, but this was really a pilot project. And we have another announcement from just a couple of days ago or last week from BMW again. Now they are working with Hexagon here in Germany and Switzerland, and they are doing once again a pilot. So the progress have been impressive. The robots are so much better now, but we are still doing pilots. So we've had these pilots again and again. So why are we there yet? So one of the things is this scaling gap, basically how to actually reach the level of robustness and the level of reliability that we need, for example, in industrial use cases. And this is a bit what they call the demo illusion. And this is not what I would say just people who are not experts in robotics maybe get fooled by, but also, I mean, I recognize that I've been fooled by demos many times, and when I talk to my colleagues, many of them as well. So for example, this is one of the latest works from NVIDIA. So this is from December. And it has this very nice demo where the robot is able to pick up a box, put it in a trolley, push the trolley, and then take the box out into the shelf. Now, this is impressive. If you showed me this, I don't know, just a year ago, or especially 2 years ago, I wouldn't believe that this is possible in such a short time. So I don't want to take any credit away from this. But when we see these videos, we should also critically analyze a few things in terms of real-world use cases. What are the success rates? Very often with these demos, success rates is anything from 30 to 70%. Now, you cannot have a robot in industry that fails half of the time. You cannot have 100 or 1,000 robots and doing something, and then half of them are failing half of the time. Then you need more people than robots to keep up with fixing what they are doing wrong. But beyond the success rate, what is the robustness of these AI models that we are learning? Like, how much can you change the box? Does it still work? This was discussing a bit on the fragility of the models and in terms of the data that we collect. How much can you change the scene? Can you change the color of the shelf? And most importantly, this is not always revealed, even in technical reports, how much data exactly was needed to achieve this. Because it's not the same that you needed 100 samples with teleoperation than 1 to 10,000. So in terms of cost and human resources to achieve this is very different. So in this case, for example, for some tasks like this is not super accurate, but the success rate is approximately 50%. And then it accepts 20% variance. Now, this is super vague for myself, probably for most of you as well here listening. What this means is that you can change the environment, the box, the colors, the lighting, approximately 20%. And that's really, really limited in reality. Then we have also another type of works. So in this case, this is a very nice paper from also the end of last year, Tsinghua University in China. They built basically these grippers with integrated cameras that you could put into any arm or any robot, into a humanoid, into a robot arm. You could have 1 robot, 2 robots, and the same AI model could be used across what we call embodiments. Now, it looks amazing. It's true. It works a priori. We tried it. We got the same hardware, the same cameras, the same grippers. And then when we start going through the code base, through all the documentation, you start finding things like, well, yes, it works, but the arms have to be separated by exactly the same distance. They have to be in exactly the same initial position. The table has to be exactly the same color. The objects have to be very, very close to where they are in the training data. So yes, it works. We have amazing capabilities, but the real world, let's say, transferability and generalization is still very, very limited. This is another video, I think, from yesterday even. So Xiaomi, I should mute this. So Xiaomi just released that they've done, this is actually a video that I like because I think it's a 3-minute continuous video. So not something that you see often. Xiaomi has these humanoid robots basically put in screws, and they achieved quite high success rate. I don't recall now, but if it was 90%, but quite high. Now, this is the other thing, touching on the problem on whether we need humanoids or not. Most of the demos involving humanoids, the humanoids don't walk, and these are legged humanoids. So it's not even on a mobile base. They actually have legs. Now, this is an example of the state of the art today. So really, robots in a factory is still achieving something like 90%, which I would claim that is not really scalable. So you cannot put this into thousands of robots that fail 1 out of 10 iterations. But they are still not moving. So when we introduce movement, the amount of data that we need, the complexity of the task, the amount of basically diversity that we need of the data, this increases significantly. So I would say that this is another, let's say, takeaway or thing to take into account when watching these demos. Like very often we have humanoid demos and humanoids don't walk. Now I'd like to close all these examples with what does it really take to have a robot in an industrial environment actually operating with robustness and reliability. So Figure had this use case last summer. And just to put it into context, so Figure is the startup in humanoid robotics in the world that has raised the most money, so billions in funding by now. They probably have one of the best robots, if not the best, one of the best AI models. And they were already doing for a while this pilot with BMW. And then they switched to this second industrial use case. I will show a video in a moment where the robot is supposed to pick up a package from this one conveyor belt and then shift it to the other conveyor belt on the left side here by checking which side the barcode is. Then it puts it down and flattens it. And they release, and I think it's hours-long video where the robot doesn't, like basically it probably fails less than a human. So it's really, really reliable. But Figure already had the robot, already had the AI model, already had all the data acquisition and training pipelines, all the infrastructure required to teach this robot, and already basically had everything. It just needed to teach it one more skill. So how much did this take? What did this take? Well, it took them 1 month. It took them 500 hours basically of teleoperated data they had to record, which then had to be curated and then the model trained. So probably 300,000, $500,000, maybe more than $1 million in cost just to teach the robot this one skill. And I'd like to emphasize this one thing here, because when I talk to companies especially, they are often, let's say, misguided by this idea that you just need data. This is not true. Figure here recorded 500 hours of data, but this was not enough. For today's AI models, the quality of the data matters a lot. So what they had to do is they had to put a team of senior engineers, and this is the people who actually builds the AI models. So there's very few of these people available worldwide today, I would say. These people who actually are experts into both the robots and the AI models that are trained went through these 500 hours of data and had to select the best 30 hours. And this is what was actually used to train the model. Now, you can use unskilled labor potentially as the technology becomes mature to record the initial 500 hours of data. But to go down to these 30 hours of high quality data, you still need not just skilled labor, but basically world top experts today. And this is unavailable basically to most people. But it's true. So this is what it takes today, or 6 months ago. Things have improved for sure. But this is what it would take 6 months ago to get a robot to do something like this reliably with a, let's say, 99.9% success rate and robustness. And you can see what is the complexity of the task. So you could ask yourself, are companies willing to pay $1 million in advance to teach a robot one skill like this, where again, for example, the robot is not even moving, right? Like it raises the question, do you need the legs? I'd say I'm not totally negative about that. So, I mean, it's true that if we really mass produce humanoid robots, it's a general platform. Eventually they would become very cheap. So even if it doesn't move, it might be cheaper to have a legged humanoid than a purpose-built robot. But still, at least today, this raises some questions. So I'll try to close very, very quickly because I'm over time already. But my takeaway from this presentation would be that today the physical AI and robotics landscape is fragmented. There's a lot of research put on combining these things, on improving things, on learning from less data, on learning something from, let's say, someone that just wears a GoPro in a helmet and you don't need to teleoperate a robot, but it's not there yet in terms of use cases. So the need for human data, the need for teleoperation data, and the fragmentation of this landscape, basically the things that we have, reinforcement learning algorithms that teach mobility, and then human demonstrations that teach manipulation, how to combine these two. We don't have, let's say, best practices and a good solution for now. And I'd like to close with what we are doing. So we are spinning off, as Mike said, a company from the Zurich University of Applied Sciences called Binabik, and we are working at the intersection of basically physical AI and agentic AI. And as much as I disagreed earlier with Jensen Huang, I'd like to borrow this one slide from him that I like and that he's used for many years now. So we are doing basically software for humanoid robots, and we think that we can solve some of these problems by basically tackling the application layer, not by building better models, but by building the infrastructure required to actually combine these different pieces of the puzzle and building what we call an agentic operating system that would allow us basically to use our reinforcement learning policies, something we learn in simulation when needed, or we use something that we learn from human demonstrations when required, and that we can also break down things into smaller steps and reuse modules over tasks. So I won't go much in detail. This is a bit where we are in terms of, so we are doing some pilot with a company also from the university side. So this is the humanoid. I personally don't think we will see elect humanoids in industry anytime soon. So it will probably be humanoids on wheels. But yeah, this is a bit where we are today. And thanks a lot. Happy to answer questions.
Thanks so much, George, for offering so much capabilities. I mean, it's impressive. Great food of thought. Probably opened up a word to us in terms of demystifying the hype, and great way also to build a agentic operating system with your startup Binabik. We have actually a question from Christian to you, Jorge. He's asking about safety and guardrails in embodied AI. Maybe you can touch on both at the model level and at the robotic level side of perspective to just offer to Christian a little bit more insight about guardrails and safety issues.
Yeah, thanks a lot. So if I start on the hardware side, basically the reason I don't particularly believe that we'll see humanoid robots mass deployed on legs in at least in the next couple of years, it's basically boils down to safety. So there's actually a new working group since last year from the IEEE. So really world level working group working on new safety standards for these robots, including robot dogs. This is what we call actively powered robots or something in that line. So basically they need active energy to remain stable. And this is a problem because this means that if anything goes wrong at the hardware level in terms of power, the robot runs out of battery. What if it's stuck in a staircase? It's full of people around and the robot is just running out of battery. It cannot just break in place as when you have wheels. So this is one problem. What I see that many companies like 1X and maybe now Figure are doing is trying to go towards, let's say, lighter bodies and also soft bodies. But I don't personally see that this completely solves the problem. I would not put a soft and 20-kilo humanoid anywhere near a little kid because it's still 20 kilos that can fall down on top of the kid. And on the AI side, yes, this is a very, very valid point. This is a very active field of research in terms of how to ensure safety. But basically, when we teach from human demonstrations and then we just take these large models and we feed them this data and we get them to do something specific, safety by default is not embedded in there. So how safe the model will be, it will depend largely on how good the data was. But even if we take a very, very good approach, we can still not ensure by itself that it's safe. So this is also in terms of this missing piece, this missing infrastructure and pieces of the puzzle area that I was touching. Like we have all these pieces, but we really have to put everything together. We need more layers, like adding safety on top that doesn't interfere with these new advanced capabilities. And this is one reason that, for example, AI hasn't come to, let's say, medical or assisted robotics as much, or this new wave of AI. There's a lot of more regulation, safety concerns, and we have to tackle those.
Well, that's a lot of things still to tackle, but I guess we're getting there. Let's open to the panel. Lizzie, back on board with you, and Jorge. Really looking forward to hearing two applied perspectives on embodied AI from different contexts. So for the audience, for the next 10 to 15 minutes, I'd like us to stay on that contrast and unpack what actually changes once the systems move beyond controlled setups. So first, let's just ground this in reality. Both of you work on embodied AI. We heard different perspectives in terms of understanding what's the use case, purpose-driven use cases. There's a lot of pilots and difficult to scale. So let's just go with one question. When does really embodied AI leave the controlled environment? Let's say, Lizzie, to you, to the hardware lab. What might be the first assumption that likely tends to break for you?
It manifests on the physical level, I think. So and it's probably because you have some sort of uncalibrated motor or something like that. So you'd see it manifesting on the physical level more than the software level. So I think that would be the first thing that breaks, if I could answer that question. It goes back to what I said earlier when it's about data. If you take it out of a system that's constrained and you've already trained in this environment, your model will fail. But what you will see, how to diagnose this is by looking at your physical arm and then looking at what fails first. And it manifests basically at the physical level, if that makes sense.
At the physical level primarily?
Not that it breaks, more like if you're building a robot and you have motors and all the systems in there and wires, you can easily diagnose it more often than often. You've trained your model very, very well. So you know that it'll work in this constrained environment. However, we see that our issues tend to be at the physical level. And then from the physical level, the next thing would be the model. So it's actually quite physical, the issues that we face.
Does it resonate with you, Jorge?
Yeah, definitely. I think I would say the hardware is one thing that people usually don't realize that it's a limitation still today. This is again changing very fast. So I think everything has to be taken with a grain of salt in the sense that in 6 months from now we will have much better robots, much better models again, and so on. But this is hard to extrapolate, but for example, Boston Dynamics did a very constrained demo at the CES in Las Vegas with their new robot. It collapsed once in 3 days. Now you can see this as very little, or you can see this as really very far from a robust hardware. Because if one robot collapses once every 3 days, I mean, we cannot make an average, right? It's just one event. Maybe it's 1 in 10 days in average or 1 in a month. But still, if you scale this up and think people saying that we are going to have tens of thousands of robots in production next year, they cannot be failing at this rate. So beyond the fragility of the AI models with respect to the data that is available to train them, I fully agree with Lizzie that there is a physical limitation in the hardware.
But we all agree there's a lot of public attention right now, right, around humanoids and general purpose robots. And sometimes we just often draw the conversation to, it's just AI on top of hardware, and then it should work. But in practice, when you're actually building and deploying all these systems, how do you think about the balance between the intelligence in a system and the body that sits in it? Jorge, maybe you were touching on, on Boston Dynamics and so on. So would you kind of say the balance is over into the intelligence part, because then the physical cannot keep up with that? Or how would you say that?
Yeah, yes. So basically, I think that when there is new hardware, you can catch up relatively quickly on the software side. Maybe I have 2 viewpoints in this area. So one is in terms of how we teach robots. Like, again, you could build a robot with 4 arms, but because we don't know how to teach it, or we don't have 4 arms ourselves, then we cannot exploit as much the hardware. But also something that I would say maybe I felt for in the sense that there's been a lot of hype around these dexterous hands, right? And we have dexterous hands for our humanoid robot. And we started working with a company last September. And basically they wanted to see what we could do with hands. We also wanted to see, we thought this is the frontier. And yeah, basically AI models today can be trained to use such hands. Now, 6 months later, and we've validated this with other companies and people that have gone through the same process, we've realized that actually the majority, if not all the tasks that companies want automated, you can solve with 2-finger grippers, with something simple. And this is not just about going simpler because it's enough. We started with hands. We operated with a lot of metallic objects. The hardware is not robust enough. We had like silicon pads peeling, then the sensors stopped working, the force sensors. But also because basically the amount of data you need, I would say, is related to at least 2 things. How much the robot needs to move. The more it needs to move, the more data you need. And then the more motors you have to control, the more data you need. And one of these dexterous hands has 20 or 30 motors. A gripper has 1. If you have 3-finger gripper, maybe it has 5. So do you really need it? Because now you're going to need a lot more data, a more complex AI model. You have higher chances of failure. So I'd say that there's a lot more about this balance, basically, in practical terms.
Good way to put it. And when
Yeah,
it comes
I'd
to
kind of
scaling
agree.
that type of balance,
If I could cut in, I'd kind of
Yeah,
agree
sure.
with Jorge as well, because I don't really separate the intelligence and the embodied part of the robot anymore. I see them a bit like a human with sensory organisms. The body, the model can, the physical body influences what the model can realistically learn. So in many cases, I would rather just improve the physical reality, like are we moving from 5 fingers to the 3 grips that he said, rather than increase the model complexity. a stable body would reduce the burden of the intelligence.
Right. And when it comes to scaling those type of systems, like what breaks in practice there? What would you say, Lizzie?
Messy environments.
In terms
environments,
of let's say like manufacturing, you know, it's definitely, it scales, right? Like reducing the useful components, drones and so on. Would you say like it's the purpose of solving a problem that should be scaled, or where would you go?
Yes, having some sort of like purpose-driven robot or embodied system would definitely scale. The ones that pop into mind are scenarios where humans are needed. So if you're in the defense sector, if you're in energy, autonomous drones, you want to replace humans from those ones, I think that would scale very well. What will not scale is anything, well, what will be a bottleneck is trust. And once you're trying to transfer from that technical acumen that we've developed into developing trust, is going to be hard to scale, because your robot doesn't need to work once, like Jorge said, the Boston Dynamics robot failed once every 3 days. We need something that will predictably work in a stressful environment. So the bottleneck will be trust, not necessarily technical acumen.
So instead of just going to you, Jorge, in just asking you the same questions, we could maybe mix it with a question that has been asked for from the audience. You know, when it comes to scaling in human environment, right? Mostly of us ask if they're capable, I don't know, to box a big honeydew, you know, like a melon, for example, but they're also responsible to look after humans, and there's children involved and so on. Who is accountable for those type of robot dogs or ending up hurting children? I know it's really the scaling question, but I guess that's something that's really important to our audience. And I guess it also becomes on the scaling part, right? Because on the pilot, we can definitely have that environment, but once we leave it out to the humans, that's certainly a pressing question here in the audience.
Yeah, that's a very good question and very valid concern, and I'm not sure I'm the right person to answer it, but I'd say that, yeah, this is very open. Well, we've had this conversation around self-driving cars for many years now, and I'm not sure we've reached a consensus yet as a society. So yeah, the same applies to robots. I think, I mean, I don't know, I have a few thoughts here. So one is, for example, drones, right? If I go back 10, 12 years ago, there was a lot of development around drones. We would start to see pilots and drones appearing out there. And then what happened is, partly connected, basically regulation happened, and this was partly connected to a few accidents that I mean, nothing major or too fatal, but for example, here in Switzerland, there was a delivery drone that was doing a pilot between hospitals that suddenly dropped, the parachute failed, and it dropped in a park. There were kids playing nearby. Now, nothing bad happened, but it was close, right? And then basically, so governments or the EU realized that, this has to be more tightly regulated, and we need better processes to manage this. And I would say that only now, 10 years later, we are starting to see again, basically this higher adoption of drones. So I think that something similar might happen. I hope that nothing bad happens with humanoids. I would say that it's better if we don't see, let's say, these lagged humanoid robots around shopping centers, because they are not fully ready in terms of both hardware and software. And yeah, maybe the other thought I would have is in terms of scaling. I mean, so what many companies are doing is this idea that if you just have enough data, this is enough to scale. And I think this might be a very valid approach for home robotics, because well, Figure and other companies famously have rented every Airbnb in California. So if you train your robot in 10,000 different homes, and then you go to the home number 10,001, there's a high chance that it works. But you cannot do this in industry. You cannot go around knocking the door of factories and say, hey, do you mind if I spend a week here recording data? And then, by the way, this data will also be used for a robot that will be deployed into your competitor's factory. So whatever they learned here will be also useful there. So like, for example, this data privacy, it takes another dimension, because now it's also about competition, right? Like, if ChatGPT takes our data, this is more on the personal privacy side. But if you record data in a factory and then sell the robot to their competitor too, where they basically leverage the fact that it already knows a lot from similar processes, then this brings a lot of other concerns.
Well, that's certainly a valid point on the different concerns, where it brings us basically also to the fact on where the translation fails, right? So in the case of system, when they get deployed, it goes into a product or to a program. Where do you see the translation breaking then on that side specifically? Any of you who would like to bring in input on this? So is it more like from the research to deployment?
Yeah, so that's what I try to basically reflect in the presentation as this scaling gap. So I think that we are already in a very good place in terms of going from research to pilot, but to reach the level of robustness, safety, as you said, and reliability needed to go from a pilot to a scalable deployment, then this is what is missing still today. So I would say this is the gap that needs to be closed.
One pressing question, maybe for the students and founders here in the audience. Lizzie, let's make this very concrete. Where should they be careful? What should they build, basically? And what should they not build? You know, where shouldn't they focus on so much? What would you go for?
I think we've touched upon how useful are fully formed embodied systems. So definitely constrain what you're building to, like we started with an arm, something really constrained in an environment that is useful. If you're trying to translate from research to founding and building, look into the sectors where humans need to be replaced the most, or dangerous sectors that humans do not need to be in. And if you're trying to start, open source is the way to go. It definitely took us from 0 to 108 weeks. And I feel more comfortable at robotics. So definitely open source is the way to go. It's kind of the medium that enables us to propagate our progress.
That's great. So the barrier to access is definitely open source.
Yeah.
Would you touch on quickly on that, Hoch, and then we just jump to one question about energy consumption and then sensor technologies. But what would you say? What shouldn't we build, or what should we build, Jorge?
Yeah, well, I fully agree on the open source side. And as I said, I think this is one of the key components to really reach this, let's say, ChatGPT moment of robotics, which I don't think that it's that close. In terms of what should we ask, so I think that as much as, let's say, I was maybe a bit negative on where we are today during the presentation, I think there's a lot of hope and there's a lot of potential, and we've seen unprecedented progress. And I think that if we ask the right questions in terms of how to use these robots, there's already a lot of value that we can extract today. And so maybe to summarize this, if we are trying to fully replace a person, especially in let's say, whether it's a factory or a professional environment in a hospital, I think this is the wrong question to ask. If we want to support people and really replace some of what they do and put robots to work together with people, of course, then the safety and all of this comes into play here, and with what kind of environments can we do this today safer. But I think there's already a lot of value there. So if we really wait until we have a fully autonomous robot that can just entirely replace people, then we might be in for a surprise how far we are from there. But there's a lot of value that we can get already if we ask the right questions.
Oh, Mike, you are still muted.
I'm so sorry. I'd say we have one question more. Sabina, would you say we go for the one question about energy consumption?
Yeah, definitely. This is a very important question.
There. Questions come before timing. So even if we're in Switzerland, we haven't talked about energy consumption and sensor technologies yet. Is asking HQ, thank you for your question. Furthermore, humans have many other sensors in addition to image capturing sensors. So can your view say something about the state of the art in this area?
Should I go for it? Well, I can start quickly. Basically, in terms of, yeah, it's true that AI is very mature in terms of understanding images because we have a lot of data on the internet, images, videos, while other sensors that are very powerful in robotics, laser sensors, lidars, radars, it's hard to exploit the advantages or the advances in AI there. So there's a lot of work to be done there. But I don't see this as a limitation today. Like you can already do a lot of things basically with existing approaches. If I touch on the energy side, yes, I get asked this a lot, and I personally don't see this as a big problem. Like battery technologies are getting better and better by the day, but also for most robots, you can really just put a bigger battery if you need bigger. Of course, if you want a robot that was 40 hours uninterrupted, then that's a different question. But to get a robot to go from, let's say, today, humanoid robots can work 2 to 4 hours. You can just get a better battery and do 8 hours today. And with what I see as realistic thing, which is a mobile base, like a humanoid on wheels, then you can really put big batteries there. So I'm not very concerned about that.
Yeah, we're
So
not
one
near
question
the level.
from,
Sorry.
sorry, can we just skip to another question?
Sure.
Saji is asking about the Isaac Asimov 3 laws of robotics. So what does really the future look like there? So we have like this doom theory, probably also seen as one outcome. We have one as purpose driven. What would you go for? Like, what's the future going to look like?
From what I can remember, Isaac Asimov's 3 laws were like robots should not harm or kill a human. They should obey humans, and then there was a third one that I can't really remember. But Asimov's systems were very they're not theoretical, but they're fictional, and they were made in a clean and fictional environment. But human systems are well, the world is really messy and probabilistic. So to answer like the safety and governance framework on robotics of the question, I think robotics will probably mimic sectors in sectors like the aviation or medical sector, where there are clear standards and like certifications for testing. Yeah, that's how to answer that question. So our world is very, very messy and probabilistic, so we can't really translate Isaac Asimov's laws universally to all robotic systems, and we need to have like regulated sectors. For if we're doing drones, we'll have specific rules. If we're doing manufacturing, we'll have specific rules, and that's how it would translate.
Yeah,
so the Asimov,
I
it's not
maybe
harm humans or allow them to come to harm, obey human orders, and protect our own existence unless it conflicts with the first or second laws. Just for
if I may,
what would you say?
The question was a bit more nuanced than that.
Yes, please.
The governance of Gen AI today is the wild, wild west. The US, Europe is very divided. The question was, once we start inviting physical AI into our house, the Asimov model was easy to grasp. It was 3 rules. What does the future look like when we can't even do Gen AI, which is today trapped in our machines? When physical AI is invented to our house, what does that governance model looks like? Where do we go as humanity when we start controlling that? How far along are we on that conversation and thinking about that? So that was the premise of that question. Back on mute.
Thanks for that. I would add that, well, I agree with what Lizzie said, basically. I don't think we are very deep into the conversation. And as much as I think any fear basically around the topic is valid, I think that if we take a step back and we look at the current state of the technology, there's also reasons to be not as fearful yet, and we can responsibly talk about this. I mean, like from what I saw, basically, if you teach a robot to move a box from A to B and now you change the color or the size of the box, then it doesn't know how to do it anymore. So in that sense, if you want a robot to basically be able to understand at all or put into effect at all such laws of robotics, as Asimov described, which again, they're unrealistic in our case. I mean, we are really, really, really far from there. So yes, I mean, OpenClaw and things like this have shown that generative AI is like a Wild West. But really to reach something where robots will go wild in robotics, we are still a bit far from there. It's true, there are risks, like if you bring a robot into your home and you run something, but I think the risk today is mostly about the robot or the AI model going like doing something that is not expected to do, and then the robot just goes and crashes into a wall, more than it purposely goes against a human. So.
Thanks so much. I'd say wrap it up. We have, it's 10 a.m. Switzerland, 9 a.m. respective UK. Thanks so much, Jorge. Thanks so much, Lizzie, for your very interesting contribution, for your presentation, and for basically opening up a world to us of understanding where the capabilities lie, also the friction of accessibility, of access, which lies in open source, and maybe also to have answered that a tricky question about where the future goes. That's certainly something that we'll see in future, how we gonna frame it and how we're gonna think about that. Just to mention, the session has been streamed live and will remain available on YouTube and LinkedIn. And we also commented the next aiLights sessions. So thanks to everyone who joined us, and thanks for the contributed questions. Sabine, I'll head back to you.
Thank you, Mike, and thank you to Lizzie and Jorge. So I really loved that combination of talk, exchange, and presentation, that we got some kind of discussion ongoing. And Shai, thanks for jumping in. And so I hope that we could open the discussion here, but maybe there will be some other sessions on that topic as well, I heard. So hope to see you one of our upcoming sessions at aiLights, and thank you for joining today, and wishing you a great day in Switzerland and UK. Bye-bye.
Thank you for having us.
Thanks so much from the Oxford AI Society. Bye-bye.
Bye.